All right. Quick reminder about your lab number 5. It's not due just yet, but I think it does take some time to really study the abstract classes and interfaces. Feel free to reach out to me if you got any questions about the materials I made available to you. As for your final exam, I'm going to release a guide to give you some idea about the formats and coverage, etc. I will talk about it maybe on Tuesday in the class, but I'll release the documents beforehand, so you can also take a read and ask me any questions. I'll do that. We can do that on Tuesday. And then for your programming test number 3, I will reach out to the TA over the weekend. So hopefully we can start a grading process on Monday. And I'll try to see if I can push them to really get me the result maybe within a week or so. So before your study day, I'm hoping, or before the last day of the class, we can release the result and feedback for your programming test number 3. And I sent out a polling question about exam review session. It's completely optional, but if you're interested, please indicate your preferred times, and then I'll try to see which one I can make it, right? I'll reach out to you pretty soon. But if you're interested, have a say in the polling. It's on eClass. And then just very quick reminder, so the bonus opportunity about course evaluation is going to expire pretty soon today. Of course, afterwards, you can still do the course evaluation. That's not a problem. But I'm just saying that for the bonus, you will need to do it quick if you're interested. I think that we're getting pretty close. But just for you guys in section F, very slightly behind. But, not too bad, right? Just if you're interested, give some feedback to the course or to myself. Again, I cannot see any of your comments or ratings until in January. It's not going to impact anything about your course, right? It's not supposed to be. Okay, any question about the course you want me to clarify before we talk about inheritance again? So the idea will be we want to finish off everything about inheritance today, and then I would like to have a little bit introduction about the last topic, which is recursion. All right? All right, let's now do a recap as usual. All right. All right, so last time we basically, let me just go back there and then here. There we go. So we did this little exercise about typecast, especially you want to be able to, number 1, given the Java class declaration with the extends keyword, you're able to figure out exactly the diagram here. That'll be the very important first step, right? Always double check. And then we discussed these two lines, and then we had some compilation error in the typecast. It's neither upward nor downward casting. And then by using 2 casts in a row, we are able to do upward cast and then downward cast from B to D. But it's not going to do us any good as we are going to get class cast exception at the runtime. So what did we learn from this example? Number 1, you want to be very clear about the compilation rules about doing typecasting. You can either do upward casting or downward casting, or you can do a combination of both. That's okay as far as compilation is concerned. But the more important stuff is about at the runtime. You want to make sure you're able to trace the dynamic type, for example, this case here, and then the type that you're trying to cast into, which will be here, you gotta get class cast exception, because the dynamic type cannot fulfill the expectation of the cast type, right? We've spoken about it for many times already. So review this exercise here. If you want me to go over that with you again, let me know. And then we introduce this new operator, instance of, as a single keyword. It's a binary operator. And what you put would be some object expression on the left, and then you have some class name on the right, typically. And it boils down into the following question, which will be true or false. It would be true if the dynamic type of the objects denoted by X might be pointing to some objects at the runtime, and its dynamic type. If that particular dynamic type can fulfill the expectation of Y, i.e., if the dynamic type here is a descendant class of Y. All right, just remember that's the very definition for instance of. And then we did quite a good number of examples about how you can use the instance of, especially the very typical usage of the instance of is before you attempt some typecasting over here. For example, before I try to cast Jin into resident students, to be 100% safe, I can always try to wrap it around in an if statement to say if Jin can fulfill the expectation of resident students by its dynamic type, then I can cast it. All right. So this can guarantee there's no class cast exception at the runtime. And we did quite a few more, right? And this page over here also summarizes about the different rules that you should also pay attention to. For example, if you got a variable assignment here, what does it really mean when what does it really mean when this variable assignment is valid? You can think about the relationship between B and A, right? We spoke about it. And also, what does this exactly return to you, which I just reviewed? And also, when you try to do this particular typecast, what does it really mean when it compiles? And what does it really mean when it has no class cast exception? All right. And also, once you got this particular alias, you can also assign that to something else, right? So these are the various things you really want to be very clear when you write the exam. That was something I would expect you to really know pretty well. All right. And then, yeah, just examples about instance of, right? Review them and then try them out on Eclipse. And this example here is just about when we try to put a static type gradually downwards from the inheritance hierarchy. You can see the number of expectations is simply going to increase. The lower you are in the inheritance hierarchy, the more expectation you can have on that static type. Right? That's also something we keep emphasizing since we talk about inheritance. Okay, so let's see. Okay, so that was the kind of the last topic we started on Tuesday. So that one there basically just try to combine polymorphism and method parameters. So quick recap, and then we can do one more example. If you declare an array SS of type student array, so we know that every element in the array, for example, SS at index 0, at index 1, and etc. Every item in the array has a static type students. So this is how we judge to see, for example, we got one method here. That one takes a parameter of type resident students. That's a static type. And then we try some variable assignment over here. We're trying to assign RS, the parameter, into an element in the SS array. And we spoke about why that line there should really compile, right? Just remember why it will compile. If I give you something that does not compile, you should also be able to notice that and justify. And you can see that we got 1, 2, and 3 different methods over here. And then you can see each one of them has different parameter types, right? Depending on where you are in the inheritance hierarchy. You gotta watch out for that. And the question we ask you to really summarize this page over here is to say, if you have a method call, if you're trying to call addRs method over here, and then you're passing some argument object O, the question would be, what's the range of static types of O that can make the method call compile, right? The way to judge is to really go back to your knowledge about call by value. If you remember, whenever I'm trying to make a method call over here, I can connect back to the declaration of the method being called, right? That's a callee, right? And the callee over here, we got parameter type resident students. Oh, even before that, there is an implicit assignment over here. You got the parameter RS on the left-hand side is assigned to be the O, which is the argument, right? That's call by value, nothing new. So now we can kind of go back to our comfort zone. When you talk about this particular variable assignments, when will that be valid? It will only be valid if the argument static type is a descendant of the parameter static type, right? That's something you want to also remember, right? Everything is logical. Nothing is really something you have to really memorize just for the memorization purpose, not really. And based on this principle here, we try to do a different example here. Just say, for example, here, if I say addRs, the parameter is expecting some resident students. So that means, because polymorphism, any class that's a descendant class of resident students, in which case only resident students, because it's pretty low in the hierarchy, can compile for the argument type. So that's why you see S1, S2, S3, they are simply of static type students. They are not compilable, right? You can go back to the discussion on Tuesday for more detail. So the only thing that will be acceptable will be line number 4 over here. You can see RS over here was declared to be here, resident students. That one there is going to match the parameter type over here. Or to be more precise, resident students, RS, the argument static type, is a descendant of the parameter static type. right? Got to be very careful about what we are reasoning here. All right, and then this one here is just another example here. And this one here is very interesting. That's something we're gonna do a little bit more developments. If you look at this method here, the parameter type here is students, which is on the top of the student example hierarchy. What does that mean? Polymorphism tells us the following. If you have some parameter type students, what can be the runtime dynamic type for this particular static variable parameter? It could be any of the descendant classes of that particular parameter. Because call by value, as I said earlier, is going to assign parameter into some arguments. What can be the dynamic type for the arguments? It could be any of the descendant classes of students. So what we're going to see in the next example will be, there is something called polymorphic collection, or in our case, polymorphic array. Given some static type for the array element there, dynamically, each one of them might be of different types. That's something we want to get into today as the example. All right, any questions? We're good? All right, let me continue with the method parameter. But let's see if there's anything we missed in the slides. Well, I got two examples, actually. Yeah, the first one here is going to be from slide 79 all the way to, I'm going to talk about them at one go in a way that is going to be a little bit more efficient for you to see the big picture. From 79 all the way to, just give me one moment. Okay, from 79 all the way to 82, right? That's what I'm going to do now. And of course, once after the example in the class, you can also read the slides for study. Let's take a look. All right, so that'll be the first set of example for today. Now, I want you to take a look at here. 1, 2, and 3. All right. So in each case, we have a reference variable called S and S. The static type is students, students, and students. Dynamic type is actually different. One is students, one is non-resident students, and another one is resident students, right? They're different, but they're all valid for the reason that you should know, based on our discussion earlier. And then in each case, we try to create some SMS for us to make a method call, all right? So we are calling specifically @rs. All right, so this method here, let me just highlight it. @rs, oh, that's too thick. @rs over here, @rs, and @rs. @resident students for short. And then @rs is over here. All right, so let me just use a laser just to show you very quickly. If you think about call by value, if I try to do this one here, and then I have argument s, and if I try to connect this one here back to the method I'm calling, what will be the call by value implicit assignments? It will be the parameter rs equals argument s, right? That's something we said last time. Is this valid in this case? Not really, because s over here was declared to be students. RS over here was declared to be resident students. Static type is resident students. Is S students a descendant class of resident students? No. So it will not compile, right? This is something we said last time. So you want to do the same arguments for this method call over here, this method call here, and this method call here. So that's why I got a cross over here. So each one of them at the moment to start with does not compile. Any question? Good. Let's make it compile. To make it compile, of course, we just have to make sure we can fulfill the expectation of the parameter. So what we can do is we can do downcast. We can downcast the arguments s over here from students down to what's being required by resident students. That's what we can do. So that's why I'm suggesting for each one of them, we're going to replace the line over here just by this. So I'm going to say sms.addRs over here, the same. But now S itself is not going to compile. So I'm going to downcast that into resident students, right? The cast itself is compilable because we're doing downcast. Okay, so this is a downcast. And after the downcast, this expression here is going to create an alias of static type resident students. And now when we talk about callback value again, right? For example, this one here, when we do RS is assigned to S. RS, resident students, S is not S anymore. It's actually this cast expression. That one has a static type, resident students. So now it's going to compile. All right? So this is a very important addition to what we said last time. Whenever you want to make a method call, because of callback value, you're going to have some implicit variable assignments. You want to make sure the static type of the parameter and the static type of the argument should somehow match in a way that follows the rule. All right, number one. Number two, you can do typecast in the legitimate way, i.e. either upward or downward, in order to satisfy the static type for the parameter, right, to make it work. All right, so far so good, I hope. All right, so we'll talk about two things so far. So there's one thing missing. Number one, if you only got this line over here, for example, it's not going to compile. But if you change this line over here into this line with the cast, it's going to compile. All right? Now, what about runtime? As soon as the code compiles, you got to run it. What about at runtime? At the runtime, you will have to watch out for dynamic type. You can see dynamic type over here is students. Dynamic type here is non-resident students. Here is resident student, right? They're all different. So compilation-wise, they kind of pass for the same reason. But now for class cast exception, now which one or which ones is going to give you class cast exception? That's the question. So if you look at this expression over here, right, you want to ask yourself, am I going to get class cast exception? Right? You want to think about the condition. You'll run into the class cast exception if the dynamic type of S is not a descendant of the cast type. And in all three cases, we're trying to cast into resident students, right? This is a very important insight. All right. This one here, right? It's got to be the same thinking for all three cases. Okay, given this, am I going to get class cast exception in this case if I write this line here? Basically, you're asking, can students fulfill the expectation of resident students? Not really. No, because student is not a descending class of resident students, right? So this one here is going to get class cast exception, yes. All right. If you're really completely lost, you really want to catch up, right? You still have some time before the exam, but this would be what I consider as basic for the final exam. All right. Please catch up. All right. So what about the second one? For the second one here, let's now do it again. Let's say for the second one, I don't have this line here, but I have this line. Am I going to get class cast exception? You want to ask yourself, what's the dynamic type for S that's being cast? Non-resident students. Can non-resident students fulfill resident students? No, it's not a descendant. All right? So that one there, also yes, you're going to get class cast exception. And the final case over here, you can see when I try to execute this class cast over here, into here, right? Now, resident students is a dynamic type for S. Can resident students fulfill resident students? Of course. A class is a descendant of itself. So, no. So this is the only case where it will be compilable to do the downward cast, and also it will be no class cast exception. All right, so when you study this particular example, which will also correspond to multiple slides, you want to really start with a story. Without any cast, each one of them is not going to compile. With the cast, every one of them is going to compile. However, when you try to execute them at a runtime, only one of them is going to be class cast exception free. All right, that's something you want to review. Okay, I'll leave that to you. There's another one here, quickly. Let's say we're trying to call another method here. Oh, the same method, beg your pardon. We're still calling add_rs over here. But now, what we're doing is we are passing an argument nrs. nrs was declared as non-resident students. All right, first of all, this method call should not compile because you can see the argument static type, non-resident students, is not a descendant class of resident student here, parameter, right? That one's good. It's not going to compile. So that's why you see a cross over here. Here's a question. Can I try to do cast like what I did earlier? Can I do it? At least I wanted to compile. So what I'm doing here is I try to cast NRS into resident student with the hope that the resident students now is going to match the resident students in the parameter. Is this compilation, is this cast is going to work? Compilation-wise. Okay, good. How come? Can anybody tell me? Yeah, go ahead. Yeah, for the cast itself, right? Yes, but to be more precise, let's say for the exam, right? What will be the standard answer? You want to say because NRS has a static type, non-resident students, and casting non-resident student into resident student is neither upward nor downward. That'll be the way to say it. All right, good. All right. But of course, you will see also the reasoning in the slides. But I'll just say no. Okay, it's neither upward nor downward cast. All right, so if you go back to the slides, that's this whole story for this example here. You want to combine these slides together to see what's really the flow over there. There are so many possibilities, right? All right, any question? All right, let's now move on. All right, so now let's now talk about something called polymorphic collection. This is something that's definitely advanced OO, polymorphic. We're basically trying to apply polymorphic assignments not just to a single reference variable, but we are basically applying polymorphic assignment for a collection of objects. In our case, an array of objects, right? It's not too bad, but let's not go over some example. But before that, I want to show you something you really want to also connect yourself when you study the slides. That'll be slide 83. Okay. For slide 83, you will see that, this is the question. How do you define a class student management system where we have a single array storing both resident and non-resident students rather than separate arrays? If you actually look at the bottom of the slides, you will see here, I got a link here for you, a collection of students without inheritance. All right, so if you click on that, it's going to bring you all the way back to slide 11, about 4 lectures ago. In that particular example there where we don't have any inheritance, no extends keyword, the only way we can do it will be to declare separate arrays. All right, if you remember what I said earlier. All right, that's something you also got to review. That's an important point. Without the inheritance, you just have no polymorphism. So you don't really have any flexibility about storing things into collection. So the only thing you can do is to declare an array for every separate class. But, okay, how do you go back? Okay, you see polymorphic collection, right? If you click on that, that's where we are. All right, so these two slides, you also want to compare and contrast. That really shows you the benefits of having inheritance, which is why we spend so much time talking about the reasoning behind. All right, so for this one here, we're going to do some tracing. But before that, let's see how the class would look like. Okay, let me just go there directly. Okay, let's look at the class structure itself. All right, here we got student management system, and then you can see we got a single array called students, and you can see the static type for every element in the array is students. That much should be no surprise. So I can just get this one here, students. I can get a little bit thinner. So student here is the static type for every element. So this one here is the static type of each element in the array. Okay. And then let's see what the pretty simple class. We have only a single array, and amazingly, what we're going to see is at the runtime, we are able to store both resident students and non-resident students in the same array. Okay. We have a single method here. You can see the parameter type over here is a students. It's very, very accommodating. What does that mean? Right away. When you actually got students over here, that means when you try to call this add students method, what can be the static type for the arguments? It can be any of the descending classes of students, right? This one here, you want to think about polymorphism right away. Guys, hello, please. Polymorphism here tells you that dynamically S can point to descendants of the students. Right? It's a very important realization, first of all. Polymorphism. All right, dynamically can be any of the descendants. All right, and then you can see we got some variable assignment here, and this one here has been already explained. You know, in the previous example, you should really ask yourself, why is this valid? Okay, I'll put a question mark here, and you want to think about. All right, think about it. It has been explained already. And then we have another method over here called register all. In the non-inheritance version, we need to have multiple loops to go over multiple arrays. But now we just need one single loop. Doesn't matter how many kinds of students you have. Doesn't matter. So here we got a single loop, which will go over every element in the array. And look at this one here. All right. This is also a very important line to see. We got students at index I, and then we call register method. All right. And register method itself is not that exciting because if you recall the hierarchy there for the student classes here, you can see there's only a single version for register, which is inherited to here and also here. The more interesting method we're going to see will be get tuition, because that one there really has different versions between the two subclasses. Right? That's something we'll see in a moment. Okay. But I just want you to know over here at the runtime, student I. That's something we're going to see. Student I over here, we know that its static type is students. That's what it declares to be. But the dynamic type for student I, this really, again, goes back to polymorphism. Given that this is static type is students, what can be the dynamic type? It can be any of the descending classes of students. It could be resident students, or it could be non-resident students, as we'll see. All right. So once you study through the subject here, and every time when you know that this student here is part of the hierarchy, you want to know right away what's the consequence when you actually got students as the static type for the parameter here, and also as the static type for some array element here. That's something you want to think right away. But we're going to see exactly how things might happen. That's very important. And to really save some time, I already got the diagram almost drawn. But before we even trace the code, let's see exactly the diagram we are talking about. We got student management system, and then we got SS, which correspond to this student array, right? And we got array over here. You want to think about each element of the array was declared to be of static type students. However, somehow dynamically, index 0 is pointing to resident student objects as dynamic type. Index 1 is pointing to another dynamic type. But that's okay, because both of these are descendants of the static type student here. That's important to know. All right? But how do we make this happen here? The key method to really make such polymorphic collection really happen, meaning that we got different dynamic types for every element here. The way to make it happen is really this particular method here. where the parameter type is students, which will allow any arguments of static of the dynamic type, resident student or non-resident student to be passed. Okay. All right, and then we'll do some instance of checks in just a moment. But let's now try to trace the code very quickly. All right, very short, just a few lines. All right, so now let's take a look. From line number 1 to line number 5, it will be very straightforward, but let me just tell you what it is supposed to do. From line number 1 to line number 5, all right? These ones here, we are creating RS and NRS, right? We got RS and NRS. RS, dynamically resident students, NRS, dynamically non-resident students. And then we set the discount rate 1.5 and premium rates. Premium rate 1.5, discount rate 0.5. And then we're creating an object SMS over here, and it simply has an array over here, right, from 0 to 99, right, some size over there. And one more thing to really note here. Every index, for example, index 0, so here, let me put it here, right? It's important to see that. So this SS at index 0 has the static type students, right? You got to remind yourself. Similarly, for index 1, index 2, all the way to the last index. All right, so let's now start tracing from line number 6 and line number 7. All right, what does line number 6 do? It's going to call add students, which is over here. And then it's passing an argument of type RS. RS, you may just want to make a connection here right away, right? This is the method call. And this one here is the method being called. And then we can try to connect them right away. So this will be your call by value. In that way, you're going to have the parameter S is assigned to RS, right? That's also something very important to note. And I'll leave it to you. This one compiles, all right, for the reason that we explained earlier. But what does this do? This one here is simply just going to execute these two lines of code and simply assign S over here, which is the parameter, which will be a copy of the arguments. So that means eventually it's going to make sure we assign index 0 to this element here. Right? For the detailed tracing, you should really try to go over. That's something we also covered earlier about how you go over the call by value. So what you really want to convince yourself would be by executing this particular argument here in the method call, we're going to assign RS, which will be copied into S because of call by value. And we're going to make it being pointed to by the index 0 of the array. That's why we got this. All right? That'll be the first add student execution. And the second one here will be very similar, but now we're going to put it in index 1 over here. All right, so these are the two most critical lines to really understand, these two. These two lines are how we create polymorphic collection. Okay? And you can do some checks right away. Right? You can see I'm trying to do instance of checks over here. Right? If I try sms.array, sms.ss, I will do index 0, and which is here. I will also do index 1, which is over here. Right? Just notice that. One of them is index 0, the other one is index 1. Okay, I can use a different color here. What about index 1? All right. You can see index 0 here is pointing to some objects of dynamic type resident students right here. Index 1 is actually pointing to an object of dynamic type non-resident students over here. Right? So now, if you try to do instance of check, what about SMS, this object here, which is here, instance of non-resident students? True or false? False, right? Because this guy here cannot fulfill the expectation of that. All right? What about this one here? The same objects, instance of resident students. Yes, right? And this one here, what about this one? This one, object here, instance of students. You basically want to ask, is this dynamic type a descendant class of students? It is. All right? So what you will get would be the first one here would be false. The second one here will be true, and the third one here will be true. All right? If you do a similar comparison here, all right? So here I'm talking about, on the left-hand side, this particular object at index 1. That object here, instance of non-resident student, true, right? And instance of resident students, can this fulfill resident students? Not really. It's not a descendants. Can this dynamic type fulfill students? Yes, it's a descendants. All right. So the final answer will be this will be true, and this will be true as well, but the middle one there will be false. All right. So important for you to really see how we can apply the instance of to check the dynamic types, especially the left-hand side, the left operand for the instance of are different. Potentially, they may have different dynamic types, which is the case right now. All right. All right. So what's the most important takeaway from this page over here? Number one, understand what polymorphic collection is. You have the static type for each element type here being students. But the dynamic type is simply a descending class of that particular static type. That's polymorphic collection. Number two, you want to see how this particular method here allows different dynamic type to be added to the collection. Number two. Number three, if you try to look at the individual elements in the array and try to use the instance of, you're going to have different answer because dynamic types might be different. All right. So many things in this particular example, but it does tell you many things important. Okay, question. Okay. Good. All right, so after this, I'm also talking about one more thing. We talk about method parameters, and then let's now talk about return value. That's going to complete the picture. Okay, return value. Okay, that's a polymorphic array or polymorphic collection to be more in general. Okay, so if you look at Java library, so basically any collection like an array list, linked list, or tree map, whatever, they're all polymorphic for the same reason. So you really want to understand the difference between static type and dynamic type. Okay. Okay, return types. Let's now do another one. Okay. This one here just a small application of the polymorphism. Okay. So let's say we got student management system, the same class, we got the same array over here, right? And then we have the same as students, which can create the polymorphic collection, right? And let's say we have one accessor over here. The accessor will be just get students. I want to get the student objects that store at index 0 or index 1, index 2, store at index I. And then the return type over here, think about the return type here like a static type, like a students. Again, the return object here can also be polymorphic in the sense that when I declare the return type for this method here, it's students. The return object's dynamic type can either be resident students or non-resident students, basically the descending classes. But how is this going to happen, right? So we have some return value over here. I just declare some local variable, just matching the return type over here. Just easier for us to see, all right? Just return value here, students. And then this one just to like a safety check, just to say if the I is not a valid index, we're going to throw some exception, right? That one's fine. And the else part over here is pretty simple. I simply say the value I'm going to return, which has a static type, students over here, right? You can see that in line number 5 over here. And then it's going to be assigned to a particular index in the array. This is okay, compilation-wise, because SSI is going to correspond to the static type that's declared in line number 2. Right? You can see where the cursor is. And that one there is going to be descending class of the static type for S, which is declared to be student as well, right? Over here, sorry, over here, line number 5. Okay, let me just show that to you quickly. Right? It's a simple method here, but it does require some application of what we learned earlier. So if you look at the local variable here, students, right? So you can see we are now trying to assign S to be something. And SSI is corresponding to the students over here, right? You're basically asking yourself the question to judge whether this should compile. SSI, static type should be students. Is it a descendant class of the static type of S here, which is students? Of course, it matches even, which is even better. All right, so that's the method. And then we return S. All right, that's the method. What I want to show you by some code over here is to show to you the return value itself can also be polymorphic. Again, what do I really mean by polymorphic here? By declaring the return type to be students, which is a static type, by being polymorphic, I really mean the dynamic type of the objects that's returned by this method here can be any of the descendant classes of students. In this case, I'm going to show you some return value could be dynamically resident students, and some dynamic type could be non-resident students. That's what we'll see. Okay, let's now take a look. Again, I already drew the diagram pretty much, but let's see what we're going to have. Okay. So from line number, I don't have a line number here, but that's okay. So for these lines up to here, all right, they're pretty straightforward. We're just creating different student objects over here. We got RS, we got NRS. That's fine. Let me show you the diagram here. So we have some polymorphic array. And then you can see index 0 got resident students. Index 1 got non-resident student. So to see how exactly we build this one here, you can look at the previous page. That's what we just talked about 5 minutes ago. What we want to do now is to trace the code. I'm just going to do this block over here, and then the second block and onwards will be up to you. All right? The way we trace these two will be very similar. It just has different dynamic type. Let's do the first block in detail. All right? So the block I'm going to do will be this block over here. This one here. Okay, just this block. Okay, let's now take a look. Okay, so what we have is we got some student S, local variable, and we say, excuse me, we say sms.getStudent0. All right, so this one here is going to call some method. GetStudents was defined here, getStudents. And then here we pass in the argument 0, meaning that we're going to return S, which is going to point to SS at index 0. All right, good. And then if you look at the SS array, what's really stored at index 0? Index 0 is pointing to this object here with this particular dynamic type. This one illustrates polymorphism because even though we declare the static type to be students, but dynamically what's being returned back to us is actually an object of dynamic type resident student. That's a new bit for this example here. All right. So once you assign this particular return value to S, you're going to have S just pointing to this object here, right? Think about the S over here. That's the most important thing to understand when you try to trace this example here. And then when you try to say S instance of students, that should be true because resident students can fulfill students, and also resident student can fulfill resident student as well. So that's why you can see I use some logical operator here, right? So both of them is going to return true. On the other hand, this one here, when you say S instance of non-resident student, that one should be false because dynamically it's a resident student, right? It's not going to fulfill. Finally, if you look at this line here, s.getTuition. So s.getTuition, you want to recall dynamic binding, which tells you that the version of the getTuition that's going to be called depends on the dynamic type of S. because currently S is pointing to resident students dynamically. So we know that the resident students version is going to be called using premium rates. And when you do your exercise for the second block over here, let me give you some very high level highlight. When you try to trace this block instead, everything is going to be the same, except when you try to do this method call here, get students 1 as opposed to 0. It's now going to return this object back to you. That object there has a different dynamic type, which is non-resident students. So S is going to be reassigned to this object here. And then when you try to say, for example, S.get tuition, now which version is it going to call? The non-resident students version. All right, so that's the essence for this example here. When you declare your method return type to be some class that sits somewhere in the inheritance hierarchy, because of polymorphism, dynamically, what's being returned from the method can be any of the descending classes of this student here. All right? It still follows pretty much, the consistent story that we talk about inheritance. Expectation, and also you want to talk about, descendants, ancestor, right? You want to make sure you kind of manipulate them smoothly. All right, question about this example. All right? Guys, are you sure? We don't have that much time, before the exam, so I want to make sure you can use me as much as possible, right, during the lecture. Really study this, right? So you really want to go through this. My expectation on my students usually on the exam is they should know inheritance very well, because that's really what you want to know about OOP before you can move on with your study. So we have some time, okay? Okay, study that, and then let me know if you got any requests about going over the material later. All right, once we're done with this, we're almost done with the inheritance. Let me do a little bit more, 5 to 10 minutes. We'll take a short break, and then we can start a new topic. Okay. All right, so if we go back to the slides, that's the example we just talked about. The slide also got some written nice comments. You can also read over. Okay, that's the code we just traced. All right. Okay. And then, so that's about polymorphic array or polymorphic collection. All right, so this page over here is something I believe I summarized in one of the pages. Okay, but let's now go over that. We're almost moving towards the end of the inheritance discussion. Let's now do some reflection. We got static type, we got dynamic type. When to use which? When do you use static type? Simple. If the question is only about compilation, does your Java code compile and be run? Static type only. Because inferring dynamic type, remember that A+ challenge, which is simply infeasible, is something undecidable problem to be known, right? So this part here is only for your knowledge, okay? What about dynamic type? It's a little bit more complicated. You can think about every time if the question itself will kind of require you to really do a little bit tracing to see the runtime behavior to answer the question. That will be dynamic type, okay? And the typical scenario would be, you want to know, for example, which version of the method that's going to be called, for example, get tuition, right? Which version should be called. And also, whether or not the class cast exception should occur. That's also something you want to refer to the dynamic type to decide, right? So these are the two typical examples for our context. All right, so that's a summary page. And of course, you don't just memorize this principle. You still have to understand the expectation, things like that. All right, so this summary here is a little bit dry, but that's also very valuable. I'll go over one of them with you. The others will be interpreted the same way. This one is to say, if you ever have the need to somehow implement your own programming language, there's a course called 4302, Compilers and Interpreters. For engineering students, I know typically you may not have the scope to take it, but just for your knowledge, if you ever have to write a program that's going to process programming language, there is something called semantic analysis. One of them is by doing type checking, which is what the Eclipse compiler will do for you. And here I'm just listing some typical rules that you will have to check if you're implementing the compiler. Of course, that's not really what we're doing here, to implement a compiler in the course. I will just go over one of them with you. Okay, so that's the just some example rule. It's not really exhaustive, but let me just go over one of them with you. For example, let's say this. Let's say this one here. So this one here is saying, whenever you have some variable assignments over here, and then the left-hand side is a variable, of course, and the right-hand side is a method call. And the method call is taking some arguments y, and the context object is x. All right? Now, what are the rules that are necessary for the compiler to check whether this method call should be compilable? There are several things, more than you might imagine. Number one, the method m here, is it part of the expectation of the static type of x? All right, so that's the first one. Is method m defined in x's static type, m here? For example, if you declare x to be a let's say students class, and then can you say x dot administer, for example? That's one of the methods in the vaccine example, right? It's not. You cannot do that because the method is not declared over there. So that's the first one. And the second one there, you want to check to see y here. You want to make sure the arguments actually has its static type being a descendant of the parameter for this method, right? That's the call by value that we spoke about. All right, that's the second one. And the third one here is this particular method call is going to return some type, which is declared as a return type, which we just spoke about. The return type over there should be able to fulfill the expectation of the static type for z, right? That's another thing, because you want to fulfill this particular variable assignments. Right, so these are the three rules that you will have to check to see whether this particular variable assignments, where the right-hand side is a method call, should compile, right? So these are also the kind of stuff you want to force yourself to think about in detail. That really shows understanding about what's involved. You don't really just write something there. If you got errors, you just try to guess how to fix it, right? You should be very careful when you write the code. All right, I spoke about this one in detail. You can also take a look at others. All right, that's also on the slides. All right, any question here about this rule? Okay, and then I got two more things, and then we can take a short break. And the next one here will be also very useful. That one just go a little bit about how dynamic binding is going to work when you got multiple versions of the method along the ancestor path. So what do I mean? Let's take a look. Yeah, this part here just repeats what we know about. The object class is the top of the hierarchy. And also, let's now revisit the equals method a little bit. That's actually one of the questions that was brought up, during the office hour or when I answer you guys' question outside the class. And now I can answer that more appropriately. We're going to talk about equals method first, but there is another method you also have been using, which is called toString method. All right, I'll speak about toString just in a moment. Let's talk about the equals method. Let's say this. We have class A. We got B extends A. We got C extends B. Very simple inheritance hierarchy, right? You can imagine it could be more complicated, but the same principle should apply. And implicitly, that's why I put a dash. Object is the superclass of the top of the hierarchy, right? Of course, you can say B also extends object, C also extends object. Technically speaking, you're not wrong, but don't do it. You're just going to make things a bit more complicated for you. All right, so now what we're going to talk about is, let's say we have this default version of the equals, but none of A or B or C has chosen to override equals, let's say. There's only one version. And you actually got C1 and C2. What we want to do is C1 dot equals C2. I want to know which version of the equals method is going to be called. All right? And according to dynamic binding, the version is going to be determined by the dynamic type of C1. Right? So what's the dynamic type for C1? It is C. Over here. So when we execute this C1 dot equals C2, now, is there a version of equals in C? Explicitly, not really. So what's going to happen is the runtime is going to go up one level, its parents, along its ancestor, basically. Does B have any explicitly defined? No. Go there. A? Also no. So you go all the way up to objects. That's how it works at the runtime. As soon as you hit the very first overridden version of equals, you're going to execute that one there. We call the version in the closest ancestor. You'll see one example in a moment. All right, so for the first exercise here, it's going to invoke the object version. All right. And let's now say we change the setup slightly. We still got C here for we still got C1 dot equals C2, right? And C1's dynamic type is still C. That one doesn't change, right? So I will still highlight here. The change will be, let's say we have the equals method overridden right here. So which version? That one's pretty easy because C1 dynamic type is C. You got overridden version here, so you call that version right away. That one should be pretty straightforward. All right, C. What if I got something like this? Apparently, I have, again, dynamic type C here. The version that's going to be called here depends on the dynamic type of C1, which is C. C itself does not override equals. And if you talk about the ancestor of C, we actually got two versions. We got version here. I got the default version here. I got two versions over here. Visually, you can already see which one should be chosen because this here is the closer to C. So that's why it will be chosen. All right. So this equals over here is going to choose the version that corresponds to the closest ancestor. The overridden version in the closest ancestor. All right, so this might be the more complicated one, right? So it should be B. You can easily try, for example, if I add another overridden version here, let's say equals. In that way, I got version 1, version 2, version 3. Now, which one will be chosen? Still this one. That's still the closest. Okay? All right, any question about this equals method here? Now, just ask a little bit about the detail of tracing the dynamic binding. So you want to make sure if there are multiple overridden versions along the ancestor classes, the one closest to you, the dynamic type, should be chosen. All right? All right. And then one more slide about toString, and then we're done with the inheritance. Okay, we still have some time for recursion. Okay, let's see here. Yeah, this is something I just said about different cases. You can read it through. And mechanism here about getting the version in the closest ancestor does not apply just to equals. It applies to any overridden methods in general. Right? So it's pretty general. I'm just using equals as an example. Example 1. Right? That's something we just did together. All right, for toString method, not much to say. The default version of the toString, whenever you try to print out an object P1, for example, right? That one there is just going to give you by default the address. That's the toString method in the object class. If you're not happy about it, you can override it in your class, which is what you did in the lab. And then if you try that, it's going to override it. For example, I can say, I try to declare this class here and override the toString method here, right? In whatever way I like as a string. And then if I try the same block of code again, let's say P1 here, implicitly it's going to call P1.toString. And that one there is going to give me, rather than the address, but some nice, meaningful message over here. So it also has something to do with the dynamic binding. Because in this case, we got two versions of the toString. We got an overridden version in point. We also got the default version in objects. Which one is going to be chosen, right? The overridden version. The same idea. Okay, good. Yeah, you can definitely try to override the equals method and toString method for these two classes, right? If you're interested. And we're done with the inheritance, but let's now talk about what you might do to practice more. So the inheritance hierarchy for the students and also the inheritance hierarchy for the smartphones, I did not give you any source code for that. For those of you who are interested to be exploring more when you study exam, I will encourage you to try them out on the Eclipse. It's not difficult to put them in. All right. And then whenever you try some example yourself, think about compilation, right? About variable substitution, polymorphic parameters, polymorphic return value, etc. And also class cast exception, right? There's many things you can try. And then also there was another example which I'll post it, right? You can also try to modify that, try to see different varieties. Okay, that's it about inheritance. Any question? If no, why don't we take a short break? And then we're going to continue after the break. All right, so we are done with the inheritance, and now let's move on to the last topic for the course. And don't forget, for your lab number 5, it does require you to do some background study on the abstract classes and interfaces. So those two subtopics are very easy to follow through because all the principles that we spoke about for inheritance, they all apply to abstract classes and interfaces. It's only some keywords you have to learn, and that'll be it. All right, so make sure you do the background study. All right, for recursion, that'll be the last topic for the course. And the reason I really chose this one to be the last topic for the course is because, number one, recursion itself has very little to do with OO. It's not exactly object orientation. So, but it's part of the course learning outcome, so I need to cover that, which, is a fun topic. We should really talk about it. And the reason I do it also the last would be, for those of you who will study 2101 next term, data structure, it will be a much more relevant context to talk about recursion. So that's why I covered that right here. So when we do the transition, hopefully that'll be smoother, right? Because you learn that the latest, hopefully you have the freshest memory when you come back in January for the data structure course with any of the instructor you enroll in. All right, recursion. So I am going to make some very explicit expectation about the recursion. We got about 3 points-ish lectures to cover. That's enough to cover the basics. And then I'm going to give you some resources right away. That's something I will encourage you to try as much as possible. I'm going to base my exam question on some of them. All right, that can hopefully give you some motivation to really study those resources, which is completely valuable. Okay, today I just want to cover some basics, and we'll do more recursion, recursive methods, design and programming on Tuesday and Thursday next week. Okay, we're going to learn about how to solve problems recursively. I'm going to focus more on the conceptual level today, right? You always want to keep the conceptual principle in your mind, all right? And also, we're going to see some example recursions. So one category will be on the strings. The other one will be on arrays. I think this one here will be more likely to be on the exam. But I'm going to cover both, right? Yeah, if time permits, we'll talk more example. I can maybe even choose from the website I'm going to give to you. Maybe we can do something either in the actual class or maybe in the review session. We'll see. All right, so give you the resources right away. Coding Bet, all right? So the Coding Bet site, they got many, a very good collection of recursion problem, especially for number 1, okay? Number 1 there, I would say you start with that. That one there is really about the recursion, the basic ones, okay? And the number 2 there will be the more advanced one. We'll see if we have time to maybe select one or two of them. And the complexity of the example I'm going to give you on the exam will be no more than that, 1 and 2. So I might encourage you to maybe form a group and try out all the problems and understand the solution and then try to get prepared, right? That's one way to go. Or you can just come to me and then we can talk about how you solve some of them if you get stuck. A more long-term solution, which I always advise people to do if they improve on their recursion ability, is to learn a new language. The best language to learn to program recursion is something called functional language, which is not OO. All right? So for those of you who really want to dedicate your spare time, maybe over the break, to really sharpen your skill about recursion, my best advice will be you have to learn about a functional programming language. And this is a very popular one called Haskell. All right? If you're interested, that's where you should really spend your time on. That'll be the smart way to spend the time on. All right? But as far as this course is concerned, these two. All right? Haskell? No. Only for those of you who are curious about the subjects. All right, let's now talk about recursion. And today, I got about 10 minutes or so. I can potentially talk about how you can think about recursion conceptually, and we can talk maybe a part of a small example, and then we'll continue on Tuesday, dive into more details. Okay, what's recursion? Okay, so recursion in some ways is like a loop, but many people find it very hard to learn in the beginning. But once you really grasp the idea, once it clicks, it's actually a very natural way of solving things, but we'll see. Recursion is very useful in expressing solutions to problems that can be recursively defined. And recursive definition is something you already have seen in your mathematical course, like a math course. Okay, that's something I can draw some connection later. Okay, so basically, just always remember if you want to program recursion, so there are two things you always need to supply. One will be base cases, and then the other one will be so-called recursive cases. Right? I'm going to talk about each one of them in a moment. Always remember, when you want to program recursion correctly, always start with the base cases. The base cases are like edge cases for you to program right away and get a solution. And the recursive cases are usually where people are struggling, because the recursive case seems very magical, but it's not really. Once you get down to tracing, nothing is magical, right? Because everything is going to be run by the computer. All right, let's now do a little bit visual here. Okay. You want to think about when you want to solve a problem recursively, right? There are two cases here. We got base case over here. We got recursive case over here. All right. Conceptually, you want to think about for the base case. So the first one will be base case. And the second one here will be recursive case. Two cases. And base case conceptually will be you're given some very small problem. You can solve it right away. You got some corresponding solution right away. Just solve it. Okay? And what's really recursive case? It's like this. Let's say you're given a problem that's big enough. I simply don't, you can see apparently this problem here is bigger than that. So I don't have an immediate solution to that. So what I can do instead is I want to divide my big problem here into smaller problem instances, strictly smaller. Strictly here is very important. So this problem here is strictly smaller than that. This problem here is also strictly smaller than that. Each subproblem you have cannot be of the same size as the previous one. Otherwise, you run into infinite recursion. All right, just remember. So once I divide my big problem here into strictly smaller problems, this is the critical step where people got confused. All right? Here I use the word assume, which means you simply say that, okay, once I got my smaller problem here defined, I have the solution for them right away. I can simply use them. That sounds very weird, but that's something once I start tracing, I'll show you starting from Tuesday. But when you think about conceptual one, this will be the one you're going to struggle the most. All right. So somehow I got this strictly smaller problem here. I assume there will be a solution for it. Also, I got a strictly smaller problem here. I assume there's a solution for it, and etc. The final step is here. Given that I have so many solutions there, each one of them alone is not a solution for the original problem. Agree? Because they're for strictly smaller problem. But if I can somehow combine them together, I will be able to get a solution that's really for the original problem. So I really have covered every phase you're going to think about recursion conceptually. And usually, let me recap. You have to start with the base cases, the small, like a small problem instances. You do have the solution right away. Okay, that's base case, and it could be several base cases. Does not need to be just one. Recursive case will be where the problem instance is not immediately solvable. It's too big. I can simply divide that into smaller, strictly smaller problem instances. For each one of them, I simply assume I have the solution already. By this assumption, I try to combine these smaller solutions together so I can get the solution that's going to work for the ultimate problem. All right, so that's the conceptual idea for recursion. It does make sense conceptually, But once you go down to programming, it appears a bit ugly because it's kind of, we'll see example, right? All right, so that's something you can try to think a little bit about, over the weekend. And then, so this will be some very important. How do you identify there's a recursion instance in your method? Very easy. Typically, if you see a method here, but inside the method you're trying to call itself, then you have a recursion. Simple definition. If a method's definition contains itself, it's recursion. You can call the same method either once or at least once. Or sometimes recursion, you may call the same method twice, which is okay. All right, so this one here, you're basically calling M itself, so that's recursion. Calling M itself, so that is recursion. All right, that's important. That's how you identify a recursive call. And let me talk about two important aspects you want to pay attention to. At the moment, you can see when I declare the parameter type for M, it's simply I. All right? You can think about this is some given problem. Like an argument, right? Like a parameter. I could be integer, for example, 10. Let's say 10 is too big for me to solve right away. So given problem. And then you can see here, for this particular recursive call, I'm trying to call j. Presumably, that should be another integer. So here is a requirement for recursion to work conceptually. When you are trying to make a recursive call, it's basically corresponding to this particular phase somehow. We are assuming that we're going to solve some strictly smaller problem with this particular solution. So you can think about this mj over here is basically the solution for a strictly smaller problem, j. If we talk about integer, if this is 10, then this one cannot be 10 again. It got to be strictly increasing. That will be, for example, 9 or 8. All right. So this one here is very important conceptually. This one must be a strictly smaller problem. Must be. All right. And then, for example, j should be strictly less than I. Otherwise, you got infinite recursion. All right. Okay, that's good. Why don't we just do one thing quickly, and then that'll be it for this week. If you look at the slides over here, in slide number 5, so this is just a definition for the call stack, which you guys already know, right? When we talk about the exception lecture, we already talk about call stack. So I can go directly to it on Tuesday when I go over the example. And let's take a look at this one here. Okay, how about that? Very quickly. We got 4 minutes. Let's not waste time. This is the definition for that's like a hello world recursion example people talk about. So we got to talk about it, right? Hopefully in 2101, if you still enroll in my session, I don't need to talk about it again. I can talk about something more advanced, okay? But let's talk about it now. So this is the definition for factorial. I'm pretty sure you know what it is, right? From the math course. Number 1, you see the definition here. That's factorial. N factorial should be basically either when n is equal to 0, it should be 1. Otherwise, it should be from n multiplied all the way down to 1. Number 1 thing to see or to ask, is this definition here for n factorial recursive? To answer that, you want to ask yourself, when I am trying to define n factorial here, this is the whole definition. Does the definition itself contains some factorial? Does it? No, you don't see anything. You see 1 and here multiply. You don't see the occurrence of exclamation mark again. So this definition here is not recursive. All right? That's my point. All right? So this definition here is not recursive. Not a recursive definition. The reason, again, is because in the definition itself, we never refer to factorial again. So that's why it's not recursive. All right? Now, can we somehow turn this guy here into recursive? All right, I'm not going to waste your time. I'm pretty sure you know how to do it. The recursive definition will be something like this. We're going to say n factorial will be equal to 1 if n equals 0. Or it could be n minus 1 factorial times n. Something like that. You can also double check the slides. Right? It should have said, n times n minus 1 factorial, but it's the same. All right? That's the recursive definition. But the final remark I want to say, why is this particular definition here recursive? You want to see that here. This is the original problem of size n. In order to solve it, I somehow break it down into two cases. This one here is the base case, which I can solve right away. Because when n is equal to 0, I don't need to do any computation, just 1. On the other hand, this guy over here is recursive case. When n is larger than or equal to 1, I don't really have any immediate solution right away. And then you want to see that over here, when you look at this one here, n minus 1 factorial, right? You can see the factorial over here, another factorial problem. But this time, n minus 1 is strictly less than n. Strictly smaller problem. So that's something you really want to observe. In order to solve this original problem of size n, I can break it down into a problem of size strictly smaller, n minus 1. All right, that's a very important principle to apply. All right, that'll be it. And then I will start diving into the details for recursion on Tuesday. All right, see you next week.